My name is Rigo. I've been working with EPON for about a year now. So I got into Go a couple of years ago with like a small, as an intern with a small like project we were doing. But I really got the opportunity to dive deep about last summer for like about 3 months. I was on a contract and I was working with Go to build out some Lambda functions. That was my first like real experience with Go, like building something that was going to be used. That contract ended, but like my interest in Go was like peaked. So I've been working with Go on my own for the past several months, just learning here and there. I was planning to go to the Go conference, the Capital Go conference in March, but like things happened. But I've continued working on Go, and like this is like part of like what I've been learning, and like part of the journey to like learning the actual like how to use Go. I'm gonna go ahead and start presenting. Pull this up. Share. Okay. View presents. Okay. So this talk is called like Go serverless, 4 loops to WorkerPools in 4 steps. So the point of this really is to get a good understanding of Go's concurrency model and how you can build simple synchronous code and start adding Go's concurrency features and start building a like concurrent application. And I'm going to do this all within a Go Lambda. Yeah, so I think I just kind of went over all of this. So some things I'm going to go over is like what the goals of the project are, like what the approach is, what concurrency features I'm actually going to talk about, and then we're going to look into the code. So what I hope people get away from this is like we can use AWS SAM to quickly generate Lambdas. One of the features that really got me to use SAM in the first place is the local debugging. So you could spin up your app with an environment that mimics whatever AWS is currently using to support their Lambdas. And like hopefully people can walk away with a better understanding of like some of the fundamentals of like Go routines and channels. And I'll mention some other like great talks that I came across while like diving into this. But the main idea is to show how we can start applying some of those features and build something that's highly concurrent. So what we're actually going to be building is it's a Lambda function. It's going to take in some parameters, and the end goal is to generate a collage of like random colored images. So it's going to generate like a random color palette, and it's user specified. The user can specify whatever size it is, and then so we're going to generate that. And we're going to upload it to S3 and then return a simple response. Okay. So we're talking about concurrency, right? So what it is and what it's not. So simply, concurrency is the ability to deal with multiple things. Like the diagram on the top is showing like what a single core processor could look like when it's doing things concurrently. The grayed out lines are like 3 separate processes, and the darker blue line is the actual like trail of like what's like how it's being executed. It might start one process, block somewhere, jump to the next, and continue until all processes are finished. So it's not doing anything at once, or it's not doing all of them at once, but it's only doing like one thing, but it's handling multiple. And I mention this because concurrency is often interchanged with parallelism, right? They're very similar, but they're not quite the same thing. The key difference is that when something is parallel, you're actually doing multiple things at once. And it's important to note that concurrency doesn't guarantee parallelism, but it enables it. So not all problem sets can really even guarantee that you could build a solution that is parallel. What you can do is build something that is highly concurrent in the pieces that can be executed independently. And then as your resources go up, potentially pieces of it could be parallel. So you're speeding up what can be done independently, I guess. So you're speeding up what could be done in parallel, potentially. Okay. So the three main features that I want to talk about are Go routines, channels, and worker pools. Go routines they allow you to execute functions concurrently. They're great because they're cheap, lightweight threads. The best thing about this is it's all managed by the Go runtime, and we don't have to worry about manually creating, deleting, pausing, stopping threads. It's all done behind the scenes, and it's very efficient. And channels are for communicating between Go routines. And they pass values between Go routines. They're also used as a synchronizing mechanism to block or unblock Go routines. And by that, I mean you can control the rate or the flow. And the last thing is worker pools. So worker pools, it's more of a design pattern to think about Go routines and channels as resources. These are commonly known as thread pools in other languages, but we typically call the thread. So we don't have threads, we have the Go routines, and we typically call them workers. So these are great for controlling the flow or the rate of processing something. You don't want to build something that can consume too many resources and you overload the system. So it's a good way to reuse and recycle workers to handle whatever load that comes your way. Okay, so yeah, Go routines, they execute tasks independently and potentially in parallel. So they're pretty similar to kernel threads, except it's completely managed by the Go runtime. Like I mentioned before, this is all done for us, and it's pretty efficient. There's some great talks that go over more about how the Go runtime schedules Go routines. I don't have that link, but I'll add the link. So what it is, there's a Go scheduler, and there's a very efficient way to stop, pause, pause, start, and creating and destroying, pausing and stopping Go routines, and what happens when something is blocked, and what to start, and bouncing between different threads, and what should be started next. So yeah, kernel threads, when compared to kernel threads, Go routines are pretty cheap. They're usually about 2 kilobytes. The good thing is that they grow as they need to on the heap. So Go routines are cheap and they're light. So what we can do, it's definitely feasible to run hundreds to like hundreds of thousands of Go routines. And we can run these anywhere because the Go runtime is, we're not worrying about the actual OS threads and managing those. So what we're doing is getting those runtimes and stacking them on top of the normal kernel threads. So in whatever architecture you're using, we're letting the OS handle those kernel threads. And when it processes those, we'll just split our Go routines inside of them. And a good example is like the diagrams on the right. The top diagram is just like a standard OS core with 2 threads. The lower diagram is the same 2 threads, but the second one has 3 Go routines multiplexed onto them. And one thing to notice here is that the 3 Go routines are all different sizes. So that means they could be blocking, switching Go routines, and then executing another one. Yeah, and that'll just continue until like all the Go routines are done. But the cool thing about this is that you can turn synchronous code into concurrent code. And I'll have some more code later on, like really showing what I mean. The next thing to talk about is channels, right? And these are great for communicating and synchronizing between Go routines. There's a common phrase or like, I guess not theory, but like concept, idea, right? Don't communicate by sharing memory. Instead, share memory by communicating. So a good example to like highlight the share by communicating is this command here. More so like any command, but any command that uses the pipe functionality. So what we're saying here is that we're gonna run this command, echo hello world, and the output is going to be taken as the input to this MD5 function. So, and then this MD5 will do its operation and then send its output as the input to the T function. And then that will eventually just get stored in this text file. The share by communicating portion of this comes that MD5 doesn't have access to this input. It's only has access to the output. And it's the same thing for this T function. So channels do a similar thing, right? And to get a better idea of this, like we have to understand what a channel is. And I'll link some good talks about that also go like in depth and like what the channels are. But essentially a channel is just a struct. It has a few fields. In this case, what we really care about is a buffer and a lock. So when it comes to sharing by communicating, as values come in, so whenever one Go routine is sending something into a channel, it is the Go routine is accessing the channel. It's going to lock it. So we're guaranteed that only one Go routine has access to this channel at a single time. So it has access to it, then it's gonna grab its value and it's going to copy it into the buff. We're not passing the exact value over, just a copy of it. And then when the Go routine is finished, it'll unlock the channel and then it's ready for another Go routine to receive from that channel. So when something else is ready to receive it, again, the channel is locked. And then the buffer, we're extracting the value. We're extracting a copy of the value from the buffer. And by doing this, only one thing has like direct access to that value. So that's something that kind of guarantees the safety. There's never going to be a point where there's two Go routines accessing the same value. And like that's where like some of the strength of Go's like concurrency model like really comes. It's between these channels and Go routines, and like finding a way to kind of design a system based around these. So, and then we have like worker pools. And these are mainly just, you could think of them as a design pattern for handling Go routines and channels. And there's really only four main parts to this. There's a collector, right? Something that turns in like, accepts some sort of request, turns it into a piece of work, and then stores it in a queue. An actual like pool of a queue of work or a pool of work. A dispatcher that distributes this work to the first available worker, and then just a pool of workers. So if we look at the diagram, we see that this C is generating some work. I'm calling these T's for task. So as a task comes in, it's being stored in this task queue. And then this dispatcher will pull off some task, some piece of work, and then just hand it off to whatever worker is available. The worker's gonna do its job, do its thing, and then notify the worker it's done. And it's gonna become, it'll either, it'll just continue until it's finished, until all of our work is complete, and then it'll get shut down. Couple things here is that these workers like aren't perfect. You have to do two things to watch out for, are like leaky workers and like idle workers. We could have a long-winded application, and we could just continually create more workers and taking up more resources if we don't forget to like destroy them, or if we have them as another channel, like a buffer channel or something, we can destroy them. We should destroy them. Okay. So what are we actually like building here? So we're gonna use Go, and we're gonna use the AWS SAM model. And we're gonna generate a collage generator. So what we're gonna do is gonna have this, this collage generator, and we're gonna specify like 3 separate methods. We can have like a simple like iterative approach, nothing fancy, just like some pretty basic code, basic Go. And then we're gonna start introducing some Go routines and some channels, and we're gonna flesh that out. And then we're gonna move into like a worker pool. But the main idea is that the same pieces of code that I'm writing for the simple iterative approach they're going to be reused. I'm going to reorganize the code, introduce a couple pieces, but essentially it's going to be the same main pieces of work doing this work, but just in a concurrent way. So some like on the right-hand side, we have a couple images. This is the like expected output, just given some like however many columns we want and however wide we want each grid to be, each like cell, it's going to generate some image. Okay, generate in Lambda. So the SAM comes with a pretty handy CLI, and you could quickly spin up a new Lambda. And like this is the command, just do run init. It supports like the Go runtime and a bunch of others. So that just kind of builds up like the skeleton for our Lambda. And what that includes is a makefile, README, like this is our file structure, like a main and a Lambda handler in the main, and then some tests, a couple basic tests. The other thing here is the actual template YAML. And this is mainly CloudFormation scripts to actually spin up the infrastructure for your Lambda. And you also have a very handy deploy method, and you could pass in like a dash guided option, and it'll show you everything it's doing, from like making IAM roles to just setting up all your infrastructure, and it'll show you in a pretty like nice looking way. Pretty handy. So I already did this, so I'm not gonna show that. Just get into the code. So this is kind of what I'm expecting, or this is what I wanted to go over, right? The main plus the Lambda handler, some core pieces of code. These are gonna be pieces that I reuse in every step. And then I'm going to look at like the for loop implementation, and then slowly start adding more and more concurrency features, like landing up to a worker pool. Okay, so if you're familiar with Go Lambdas, you know you need a handler, right? So the main thing we're doing here is we're just specifying our handler for this Lambda, right? This is our like entry point, basically. So what we have here is, so I'm using the API gateway for the requests and the proxies. But let's see, so this API is going to be accepting some query parameters, right? Some of those is like what method we want to use, like the worker Go routines or like a for loop. The actual size of the collage I want, with how many columns and like the actual width. Yeah, so we're gonna extract some query parameters, do some validation, do some checking, and then move on. So the next thing we want to do is we want a buffer. This buffer is gonna be the finished collage. And it's just gonna hold the finished collage, and it's gonna, mainly we're gonna be using like the bytes. Yeah, so the like most important part here is this switch statement, and we could think of this as like the entry point to our three methods, right? And it'll just start whichever one we decide we want. So yeah, we'll kick off our actual creation of the collage. We're gonna get some result, and then we're gonna write that result to S3. And then we're gonna build a response, JSON marshal that response, and then return it to the user. Okay, so this is some of the code that I will be like reusing everywhere. So the first one is like create new canvas. This is just gonna create a new blank canvas for, this is what we're gonna be writing all the other images on top of. The other piece is the generate random grid. So what this is doing, it's gonna generate every single cell inside of our collage. And it's going to randomly pick a color, and then it's going to, Go's actually very quick at doing this. So I had to add a sleep statement. So it's gonna sleep for 100 milliseconds. And then it's going to, so once we have that color, we're gonna go through every single pixel and we're gonna paint that pixel. By the end of it, we'll have like one colored block. And then once we do that, we're just gonna return that image. Next thing we're gonna do, next thing we have is like encode image to buffer. And what this is doing, given that canvas, that full like collage, we're just gonna encode it as a JPEG and return it. And then, so I have one more thing, the actual like merge image. So what this is doing is actually, this diagram explains it pretty well. So what we're doing is this is trying to find the location of like where this next image should go in our like bigger collage. So depending on like what position or like index this is, it's gonna figure out where it goes. So what it's doing, it's gonna do some math to find out where the midpoint is. And then it's going to, since we always have the same like uniform square, once we find this midpoint, we're going to add whatever our length is and whatever our height and width is to find this max point. So yeah, once we have this midpoint and the max point, we know we can draw this new image at that point. And we're going to do that for every block in our grid. Okay, so now to the actual code itself. So yeah, we have this like create, we're just going to be doing a for loop here. So again, we're just creating our canvas. It's like a new blank canvas. It's going to be like the base for our collage. What we're going to do is like a simple iterative approach, like one for loop. And then we're just going to go back here. So yeah, we're just going to generate a random grid once for like every loop. So once we generate that image, we're going to go ahead and merge it into the bigger image. So we're going to do that X number of times. And by the time we're done, we're just going to encode that image as a buffer, or yeah, encode the image as a JPEG and return it. And then we're going to return that buffer. And like that'll be it. Okay. So this is like all the main pieces to the code. And now like the idea here is to like, how can we restructure this to start doing things in a more concurrent way? So if you want to think about like using Go routines, like the first like candidate, I guess, to use a Go routine here is probably looking at this generate random grid, right? We're always doing this one bit of work, and it would probably benefit if we turn this into, slap a Go keyword in front of this and turn it into a Go routine. So we start kicking off however many grids we want. Each one will start working on its own to build some grid. Okay, so let's do that. Okay, yeah, so we are going to do that. One thing I forgot to mention is, so once we were working with Go routines, and I want to end result. So I already have a need for that channel because I have multiple Go routines kicking off, and I want to collect all of the results. So the only way to do that really is in a channel. So that's the first thing I'm going to make. So I'm going to create this images channel. And this is unbuffered. Yeah, it's an unbuffered channel. So now that I have my channel, I could start building a Go routine and start adding to this. So that's the next step. Okay. So what we did here is now I have an anonymous Go routine. And what this is going to do is we're still generating the same random image. This time we're just sending the result to this images channel. This alone doesn't really buy us too much because so this is all within the same for loop still. So as soon as this Go routine kicks off, we have this merge image method, and it's waiting for this. Okay, I have an issue here. Okay, so we still have this merge image here and passing the same values. The thing that I didn't change is right here. This image is still or this method is still waiting on this image, like one thing I could do is either add a receive operation from images, or receive and then assign it to this image variable. But this doesn't give us too much, because as soon as we write to that images channel, this merge image will be looking for this. It's looking for the next image in the images channel. So as soon as we write something, we're waiting for it. So far, it doesn't really get us too much, because we're kicking off a Go routine and then waiting for the result. As soon as the result comes in, we're going to kick off another Go routine, and then we're going to wait for the result. But this is getting us, this is moving us in the right direction. So yeah, the next step is actually, okay, what can we, like, what did we do here? So what I really want to do is I want to kick off all the Go routines and have them either starting to generate the channel, starting to generate their own image, or at the very least, be ready to. So one thing I want to do is like have that Go routine run on its own. So that's what we're doing next. So in this portion here, we're basically just removing that merge image. So what this buys us is all of these Go routines are now queued up, basically. So whenever we call this method the first time, the first Go routine gets called, we start generating this random grid. Before it's finished, I'm pretty sure another Go routine or a few more will have started. But they're going to block because, or actually, they're all going to kick off. A handful of Go routines will probably kick off before this like for loop finishes. But at some point they will block because our images channel is unbuffered. So there's only enough space for one image. So what this gets us is that we have a bunch of Go routines queued up, and only the first one to generate its image can actually store that image. But it also lets us move on. So the other thing we have here is this for loop. And we still want to keep track of how many images we have. So the actual for loop doesn't change much, just like whatever's inside. So what we're doing here is, as an image comes in, we're going to just assign it to this image variable, and then we're going to pass it along. But as soon as we assign it, we're going to free up the images channel and allow for another Go routine to finish doing its thing. So there isn't too much of a difference between like these two like last slides, but it's enough of a difference that we could have all of these Go routines ready to fill the buffer whenever like it's available. Yeah, so from here, we could start thinking about what do we need to do to get to like a worker pool. So one thing we could think about is like, so a worker pool or a worker, we want as many pieces working independently as we can. So we can think about giving a worker most of this like actual work, like generating the image and actually merging the image in. So we'll take a look at that. Okay, so the things that have changed here. All right, so if we look at the parameters themselves, at these variables, sorry, the only thing we've added so far is, so we've added this jobs channel, and we turned our unbuffered channels into a couple of buffered channels. And we're going to increase the buffer to be the same amount of like images that we want. So in this first for loop, what we're doing is we're going to spin up our workers. So in this case, we're going to spin up however many workers we want. And its job is to generate an image and merge that image back in. But as soon as we kick off these workers, they're just going to be sitting and waiting for work. So the next loop is going to, now we need a way to send work to the workers. And we're going to be doing that by this jobs channel that these workers also have access to. So we know how many images we want, so we could just spin up a job for each one of them. And as images hit that channel, the first worker that's ready is going to pick up that first job, and it's going to start doing its thing. It's going to, and the jobs will keep flowing until we get all our images. Once we do that, we can just like close the images. So yeah, that's going to happen. So as images are coming in, our workers are still doing their thing in separate Go routines. If we stopped there, our method could end early, because we have a bunch of separate Go routines. And if we didn't have this last chunk here, they're all working independently. And if we're not waiting for them to finish, we can move on without them and take whatever work has been done. So one thing we want to do is actually wait for the workers to finish working. There's a couple ways to do this. I'm going with like a simple approach of like waiting for all the images to come in, for all the jobs to come in. Another way to do this might be to use a wait group, and wait groups could be, it's something that would be passed into the worker and then incremented. So every time you start a new worker, you would increment this wait group. And as a worker finishes its job, we start decrementing this wait group. And outside of this, we would do a wait group.wait, and that kind of notifies us that our wait group still has jobs being done. But instead, I'm just going to be, I'm kicking off another for loop to keep things simple. And I'm just going to be popping off images from the images channel as they come in. So yeah, this will continue until I have all the images that I want. And it's going to allow all the workers to finish doing their job and finish processing our collage, our image. So like once that's done, it's going to just encode the image as a JPEG and return it. Yeah, that's pretty much it. So with this, I was mainly trying to reuse as much of the code as I could. And I'm going to show you a demo right now of a couple of the application. But yeah, I wouldn't recommend using this or like building concurrent code the way I did. Once you get to this point, you probably want to restructure your code. But the great thing about worker pools are that they're not always going to be faster than just using like Go routines and channels, but it might be, depending on like how you structure and design it, it might make more sense and be more readable. Yeah, so I'll go into the actual demo right now. Yep, it's QA. So I'm going to go into, oh, had it started already. Okay, gonna clear this. So yeah, first thing I want to do here is just, so I already generated the app. What I want to do now is just build it, and I'm going to use this make build, and it's going to build the application. For now, I just want to use the local debugging tool, so I'm just going to do a SAM local start-API, and it's going to kick off. Okay. Let's see. Okay. All right, so this was, first method I'm going to try is just like the basic for loop. I'm going to ask for a image that's 5 by 5 with a cell width of 50. And yeah, I'm going to show you this in the back. As we're running our application, we could see like any logs that come in. So it's very handy, like very useful. I do enjoy using this thing. And yeah, it's just using Docker to build up like whatever like Lambda like, or might even, I'm not sure if it's the actual Lambda images that they're using. But we're building our application against something pretty close to what AWS is using. Okay, so I just generated an image and it created a 25 images, and with a grid size of 50. We're using the for loop method, and it's going to tell us about how long it took. So about 2.5 seconds. Okay, okay, there we go. Okay, so I just generated an image using the for loop. It made just a 5 by 5 image. Next thing to show. So now I want to use some Go routines and channels. And building the same size collage took 242 milliseconds. Okay, sweet. Take a look. Okay, yep, it definitely built. Cool. And now let's take a look at that worker pool. So worker pool looks like slightly faster, but not too much. Same image. So let's see, a 50 by 50. So Oh, wow, that's big. All right, cool. So like, yeah, here's the Lambda. Built this in about 700 milliseconds. Let's see how long it takes the Go teams. Go teams, I think might have been actually faster or as fast. But yeah, it's the same image. And then just because I'm curious. Okay, so I probably timed out. All right, so yeah.
Awesome. Well, thank you so much for presenting, Rigo, and we'll be looking forward to seeing you all next month.
Yeah, thanks for having me. Yeah, definitely looking forward to that other DC talk.
Awesome. Yeah, and thanks for sharing that. Great. Have a good night, everybody.
Yep.